Hi team, welcome to Wiggins Maths. In this video we're going to be introducing the concept of arithmetic series. Okay, so the first thing to say about a series is get that formula book open. Okay, do not neglect it. Got lots and lots of information in here. Of course we need to know how to use these formulae, but a lot of the information is here. So firstly, what is a series? Well, what I've got written to begin with is an arithmetic sequence. As we'll have seen from the previous video, we know what these are already. So what makes a series? Well, a series is the sum of an arithmetic sequence. So instead of it just being a list of numbers 5, 7, 9, 11, 13, etc., it's 5, add 7, add 9, add 11, add 13, and so on. So this allows us actually to be able to calculate an arithmetic series really quickly. So we're going to look at an example to begin with, one that you might think will take quite a long time, and then we're going to have a look at proving why it's true. So the sum of the first 50 even numbers. Okay, whew. So notation, we use S to represent sum, and I'm going to write subscript 50 because we're looking at the first 50 terms. So let's just do this sensibly to begin with. So that would be 2, add 4, add 6, add 8, and the last number, the 50th even number, is 100, right? So it might not be particularly intuitive at this point, but just go with it. What we're going to do is we're going to write it down again. But this time, I'm going to write it in reverse order. Which may seem a little strange to begin with. We're now going to add these two things together. So this is going to give us 2 lots. But here's the really clever bit. We're actually going to get 102 every single term. So it's actually 102 lots of, well, it's 50 lots of 102, isn't it? So now if I divide both sides by 2, I'm going to get 51 multiplied by 50. 51 multiplied by 50 is the sum of the first 50 even numbers. Okay, so that seems a little bit strange. So we're just going to have a look at why that is actually true, and the fact that, you know, we've got the formula in the formula book which we can use. I've not used it here. I'm just going to show you exactly why it works. So this is the formula that was in the formula booklet. So this was where we are to find the sum of an arithmetic sequence, so an arithmetic series, and it has got n terms. So it's important just to make a note of n is the number of terms, a is the first term, and d is the difference, okay, the arithmetic difference, and this only works for an arithmetic sequence. So the first term is a, the second term is a plus d, the third term is a plus 2d, and the nth term is going to be a plus n subtract 1 d, right? So we're going to do exactly the same as we did before. We're going to reverse it. Don't worry, the only time you'd ever have to actually do this approach is if you were asked, you know, prove the sum of an arithmetic sequence. This is just showing you why it works. So that's going to be a plus n subtract 2 d, and the last term is a. So we're going to add these two together like we did before. So 2 lots of the sum. We're going to get, if you can see, every single time it's going to add to exactly what we want it to do. So we're going to get a plus n subtract 1d. We're actually going to get 2a plus n subtract 1d. And how many times are we going to actually get this term? We're going to get it n times. And then hopefully we can see, we divide through by 2, we in fact get exactly the formula that's required. Okay, so let's have a look at how we can actually use this. And this is really, really clever. So find the least number of terms required for the sum 4 plus 9 plus 14 plus 19, so we can recognise that it's arithmetic, to exceed 1,500. So that's not saying what is the term where it becomes 1,500. It's saying how many terms do we need in order for the sum of them all to exceed 1,500. So this is really, really quite clever. So we want the sum of them all to be greater than 1,500, right? So now, as I said before, this is in the formula book. Let's not neglect it. But just for now, that's what it is. Okay, so let's just write down how many terms. Well, we don't know. That's what we're trying to work out. But we've got A is 4, and we've got D is 5. So here we can say it's n over 2, 8 plus 5 lots of n subtract 1. And we want that to be greater than 1,500. And hopefully you can see what's happening here. Okay, so we're going to deal with this first. Let's double both sides. So we're going to get n lots of 8 plus 5 lots of n subtract 1 is greater than 3,000. Now if I expand this, I'm going to get 8n plus 5n squared subtract 5n greater than 3,000. And we're going to simplify all of this. I'm going to take the 3,000 across because it's a quadratic. Okay, and now I'm just going to use my calculator to find the roots of this if it were equal to 0. It's going to save me a bit of time. So the a is the coefficient of the square term is 5, the linear term is 3, and the constant is negative 3,000. I mean, of course, I could try and factorize it manually if I'd like to, but I'm not really feeling it. Okay, so n is equal to 24.1967, or it's negative 24.796. Now, only one of these actually makes sense now. N is the number of terms, so it cannot be anything to do with that. So n has got to be greater than 0. It's greater than 0. 24.1967. Okay, if I had that many terms, it would be greater than 0. So it can't be less than that. So n must therefore be 25. So if there were 25 terms in this sequence, the series would sum to greater than 1,500. Lovely. So once again, just by watching this video does not mean you'll instantly be able to do it. Practice will make you so much better at this. And of course, amateurs call it genius, masters call it practice.